Hello everyone, welcome back. We are still moving on, solving more problems in the organic reactions of alkenes. In this video, I'll more focus on mechanism of addition reaction. That's very important because if you know the rate determining step and how the addition occurs, you could also understand the stereochemistry and all that. So instead of just memorizing individual reactions, it's better to understand the mechanism of the reaction. So let's start first with this two problems here. It's asking us the addition of HBr, hydrobromic acid, is much faster in the upper compound, the diphenyl alkene, versus the dimethyl alkene. So what we're going to discuss is that when you do HBr, in the mechanism at least, we know that the initial step where the proton is being abstracted and forming a carbocation. That is the rate determining step in the mechanism of the reaction. That's why it's very helpful to know the mechanism of the reaction to determine everything about any reaction. So it's determined that this is in this case, this one is a faster reaction. The question is why? So I'm going to show you the mechanism first. So the initial mechanism of abstraction of a proton, that leaves a carbocation being formed in the rate determining step. That means CH, the carbocation is formed. Here it becomes CH2 and C6H5. By the way, you should know that C6H5 is a phenyl group. So the type of carbocation formed here is called a benzilic carbocation. You may not have seen it before, but it's called benzilic. It's more than a tertiary carbocation, very stable benzilic carbocation. So let me do for this one as well. So initial would be just abstraction of a proton, which leaves CH3, CH plus, and CH2, and CH3. So the comparison is they are both disubstituted alkene, diphenyl, dimethyl, but the diphenyl goes at faster rate. So the question is why this happens. Okay? So the most important thing is the carbocation stability is what derives, or the activation energy for forming this benzilic carbocation, meaning that the benzilic is something like this. You have C6H5, and the carbocation is formed right there. This is called a benzilic carbocation. That position, if you form a carbocation in that position, it's called a benzilic carbocation, which is much even better stable than a tertiary carbocation. Okay? So the reason why this goes fast is because it is going through a very low activation energy as compared to the metal one. The metal one goes through this carbocation, but the benzilic one goes through this. So this will give you a faster reaction. Then now the Br minus comes and attacks this, and the Br minus comes and attacks this. Overall, the addition of HBr is much more faster with the diphenyl substituted alkene. Let's do this one. In this one, this is a hydration. So initial carbocation formation would happen not on the terminal alkene carbon. Obviously, it should happen in here. So what happens is you get the proton first, the CH3 is formed, and the carbocation is formed right there, here, and CH2 or CH3. And in the second one, it takes the carbocation, the hydrogen. You have CH3, C, CH3, CH3. That's interesting. You see here a tertiary carbocation. Here also it's a tertiary carbocation. So which one forms faster? So when you look at this, for the hydration to come and attack here with the OH, the first what determines is the rate determining step, where the carbocation forms like this. So one forms faster than the other. So in case of A, or if you say B, B goes through a very low activation energy than A. The reason being that if you just look at here, this has some electron withdrawing or electronegative atom. Electronegative atom near to a carbocation is not a good stabilizing effect. So it doesn't stabilize this carbocation. So the electron withdrawing group, like this, makes it more even positive. That means more unstable. So you don't need a positive electron withdrawing group, electrons that would be withdrawn by inductive effect. This is electrons are withdrawn by inductive effect of an electronegative atom at far distance, makes that carbocation. Actually, you need electron donating groups, electron donating groups like metal, alkyl groups, electron donating group around it. So it stabilizes, it forms fast. Hence, this is the fast forming carbocation, and water comes in, attacks that, it attacks there. So this forms at higher or faster rates than the other alcohol. So for this one, the rate is slower. So these are based on the mechanism. If you understand the mechanism, that's why you could be able to tell which one goes faster. So with this next several questions, what we are going to solve, it involves around mechanism of addition of an alkene, addition to an alkene. And it's very important to understand those problems, how they are solved, because some of them, they might involve carbocation rearrangement. Some of them, they could undergo alkyl shift, and so on. So it's very important to focus on a mechanism of addition reaction in this video, that I'm going to solve more problems in the next section. Okay, moving along, now we are asked to write a clear reaction mechanism for the addition reaction of these three reactions, and show how the particular product is formed. So if we just begin with the easiest one from the top, A cyclohexene is treated with hydrochloric acid, and also acetic acid is as a solvent also, or if you are water, you will be using water as a solvent. But here, acetic acid is used as a solvent. So as I already mentioned in the previous section, that the initial abstraction of a proton, so that's the terminology you'd be using, abstraction of the proton happens like this. This is electron rich. The alkene would take off that, proton. And now the intermediate would be, I will be just drawing it like here. So the initial intermediate would be that carbocation is formed right there. Okay? Now the carbocation is a very reactive species. So the Cl- comes in. It's a secondary carbocation. Cl- can come and attack. This is how this one is formed. Very easy, straightforward. But if you just use some nucleophilic solvent or nucleophilic species also, like if it was water, or if there is anything that's nucleophilic, that could also attack that carbocation. So this one is formed because this could attack that carbocation, I will be using a different color, which is a red color I will use. So this OH would come and attack that carbocation, and it would form this intermediate. That is a COCH3. Okay. Now, still, I mean, there is a lot of different basic stuff. For example, Cl minus, or any of the Cl minus can pick up this proton, take it away to regenerate hydrochloric acid, and finally the product would be OCOCH3, which is this one. So that's formed because the acetic acid is nucleophilic enough to attack the carbocation that is very reactive. So when you are asked the mechanism of a reaction, you want to clearly justify how those products formed by a chemical intuition or by a chemical pushing of an arrows, which are logical and reasonable. So I justified how that two products could be formed. Now, in the second, when we go to B, it shows this alkene, terminal alkene, cyclopentene compound, and you have HBr addition, and the outstate, what you would see is just HBr added across this double bond, but that's not what happened here. So you should kind of be careful, but you should start from a reasonable mechanism. So HBr didn't add here. Actually, it added right there. So it should give you a hint of carbocation rearrangement or alkyl shift and so on. But let's start by just doing arrow pushing. Initial abstraction of a proton, which should lead me to a carbocation should be formed on this carbon, not on that carbon. So one more hydrogen is added now. There are 3 hydrogens now at the terminal, which were 2 here. Now you have a carbocation that is secondary. Remember, in organic chemistry, everything is interconnected. Whatever you have done in the previous chapter still applies here. So now, I think, let me see my paper. So there should be the ring is still intact, so nothing happened to the ring. So what happened to make it into a tertiary carbocation was just a hydride shift. This hydrogen shifted here, hydride shift, 1, 2, hydride shift. We have learned this before. Hydride shift is possible. Now a carbocation is formed right where we want it, here and here. So you have that species formed. Now it is stable tertiary carbocation formed. Now the Br minus comes in, Br minus, which is here already. So that would attack here and gives you the product. So the product is right there. So this is formed by a hydride shift. So a little more thinking it requires when you draw mechanism of a reaction. Okay, the last one, C. When we see here, it's almost the same. I believe this was the reagents were sulfuric acid, water. So this is a hydration reaction. So initial carbocation would be formed here, but as you know, the ring has expanded. Whenever the ring expands, you should always think of an alkyl shift. Okay, let me push electrons now. So first, initial protonation, picking up a proton. That should give me the intermediate carbocation, where I have this. and it is this. Now, that is a tertiary, a secondary carbocation. So from now, what you glean from this is that whenever you have a carbocation formation, you should think of, is there any rearrangement? So that's what always you need to ask. So now, what happens is this would alkyl shift. This whole alkyl would shift here. So this is alkyl shift. 1, 2, alkyl shift. So what happens is the ring expanded and a carbocation formed right there, and this whole thing expanded to a 7-member ring. From 6-member ring, alkyl shift resulted into a 7-member. So the ring expanded. So what happens is I have this, and here is where the carbocation is. See, you should imagine the 7-member ring. When this moves to this, the ring expanded. You have that. Now you have H2O around floating, attacks this. You would form a 7-member ring, like what we have done before with an alcohol. So I just skipped the proton abstraction step, but that is how this is formed. So these are particularly interesting because you have seen a hydride shift to form a tertiary carbocation, an alkyl shift expanding the ring, also make a carbocation, which is, this is tertiary. Here it is also tertiary carbocation. So that's how this mechanism happens, and it's justifiable why we have those products. But from the outset, you'll be wondering how that would have been formed. Okay, we'll continue more on. Okay, let's continue more on the addition reaction mechanisms. As you see, one cyclohexene type compound, a substituted cyclohexene, a hydration reaction, but giving you 3 different products. So this one starting material, and it gives 3 addition reaction products, which are all of them are alcohol, which have added 1 H plus and 1 OH minus. But the question is, how do you get all these 3 mixtures, A, B, and C, as a product? So for this, you need to know the mechanism of how they could be formed. So as I already mentioned in the earlier section, the first thing in the hydration or addition of HCl or HBr, it's the initial abstraction of a proton from the acid, from the acid catalyst. So by this, you would be forming a carbocation. Based on that carbocation, how it rearranges, you would get different products. For example, if you have this and you have this, now this carbocation can be attacked now by water to give you the different alcohols. For example, A can be formed for A, in terms of how you get A, is that you have H2O that would attack directly without no rearrangement to get 2 OH2 plus, but here you have any other. Give you a free hydroxide. OH right there, like this. Okay, that's easy. It's straightforward. The carbocation was formed, water comes in, attacks, and give us compound A. Compound A is directly formed from that. But how do we get compound B? To get a compound B, what I would envision would be, now there is ring contraction. When there is ring contraction or expansion, you should always think of an alkyl shift. That is just to drive up and get a more stable carbocation. So from this, if you do an alkyl shift of this is a secondary one. Okay, so if the alkyl shift happens here, for example, not on this one, but if you have carbocation, you can form this, right? If you just take out, carbocation can form here or here. So it can form here or here. So this one, if you want to justify how it's formed, first let's do this whole thing shifts to this. That's the secondary carbocation. It gives me a tertiary carbocation where I have a 5-member ring and I have this. This is alkyl shift, 1,2 alkyl shift. Okay? So directly, if water comes in and attacks here, so if you have H2 around, water attacks this carbocation, you would get compound B easily. Just in similar fashion what we have done before, that would be OH right there. That is compound B by alkyl shift. But if you just do this also, and on this carbocation, which is a secondary, now this is tertiary, and instead of alkyl shift, if you just do, for example, a metal shift, 1,2 metal shift, one of this metal shift migrates to this, you will have a carbocation which looks like this. Metal shifted here and one metal remaining there, but you are forming a tertiary carbocation. Now, if water comes in, that carbon would form compound C. So compound C, compound B, compound A are formed by these different mechanisms. Remember, there is an alkyl shift, there is a metal shift, and directly without any rearrangement, you could find compound A, for example. So these are the kind of things you need to remember: alkyl shift, metal shift, and so on. That is the main thing, is stability of a tertiary carbocation. This is to form a tertiary carbocation. That's the main driving force for the mechanism of this reaction. So we'll continue more. Welcome back. Now we're still moving on, solving more problems on mechanism of the addition to an alkene. Is an interesting question here on regioselectivity. The point here is you have compound A and compound C. They are adding HBr across the double bond, but they add it in a regioselective way, and the question is why. So first, let me just give you how the addition goes, and will justify why. So that is addition already. So you have that. Br right there, and OCH3 is right there for this case. And for this case, I would say, first of all, you need to know why I'm adding it right there. Here it's Br, and you have COOCH3. So no, so this is right there. It should be added, not there. It should be here. It's 1, 2, 3, 4 carbon. 1, 2, 3, 4 carbon. 1, 2, 3, 4 carbon. So here it's at 1 position there, here at 3 positions. That means 1 is adding right here, the HBr, hydrogen is added here. Here in this case, hydrogen is added here and Br is added here. So this already tells you the carbocation are formed at different positions for 2 different reasons. So let's see mechanistically how it goes. So if I just pull out abstract that proton, the carbocation that's formed is not on this carbon, obviously, because Br comes on this carbon. So the carbocation that's formed is this carbocation and OCH3. 1, 2, 3, 4. Okay. In this case, the carbocation is formed on this carbon, hence that's where the bromine comes in. So let me just draw the abstraction of that proton. Carbocation is formed right there. So it is here, and COOCH3. So the carbocations are formed at different locations. Why is the reason? So there is a concept you need to remember. This carbocation stability between these two is different. So if this carbocation is formed here, this can be resonance stabilized. Resonance stabilization forces to be their stabilization. What does that mean? If I draw a lone pair of electrons that are on oxygen, can be resonance pushed into this carbon and forms this resonance structure. So it is this resonance stabilization what makes the carbocation to form in that there. So the main concept for the top one is you can form a resonance stabilized carbocation at that position. Hence the Br minus comes and attacks that, and this is what you form. So remember again, that carbocation is resonance stabilized because oxygen is the etheric oxygen. The ether is not far, so it can stabilize this by resonance stabilization effect. How about this? This is far from this, so if this were formed here, what would happen? So that's the question you should ask. If I have put it here, let me see what the structure looks like. So if I have that, and COOCH3, this is very unstable because there is electron withdrawing. This is highly positive carbon because of the carbon-oxygen bond. It's a polar bond. It is also oxygen is pulling electrons. Oxygen is pulling electrons. This carbon is very positive, nucleophilic. So there cannot be near to it. There is another nucleophilic species. So this is not stable, highly unstable actually. So it doesn't form. So that's why this is far from here. So it shouldn't form here. So carbocation here is not a good thing because of electron withdrawing group. There is no stabilization for that. So you form carbocation here. So Br comes in, attacks that, hence it would form this. So 2 different concepts here. One is resonance stabilized. The oxygen electrons can be electron donating to this, form this resonance. Always, as you remember, if you can draw more resonance structures, the more stable that species would be. Here in this one, an electron withdrawing group. This is electron withdrawing group. this is electron withdrawing group. So this carbocation cannot be, it's already electron deficient, it cannot be near electron withdrawing group. So that's why that carbocation should be far removed from where the electron withdrawing groups are. So these are the justifications. The regioselectivity comes because of two reasons. So regioselectivity comes, the bromine here, not here. In this case, the bromine not here, but here. So two different mechanisms. So we'll continue. Let's continue more on addition mechanism and also look some synthetic strategies here. As you see here, I have an enol, meaning that it's an alcohol here and also an alkene, and it's treated with bromine. And you're getting here the cyclic ether, so it's bromoetherification reaction, basically. But how do you end up to get that mechanistically and from open chain to cyclic system? So obviously, when you react bromine, very strong reactive reagent with an alkene, the first thing that should happen is an addition reaction, right? We know alkenes undergo addition reaction, so that shouldn't be a surprise that we could do this mechanistically. First, what happens is in the treatment of bromine, the bromonium bridge would be formed. Remember that when Br2 is formed, it doesn't go through carbocation. What happens is the bromine would make a bridge. So it's bromonium sigma plus, like that. And you would have this, OH. So Br minus would be here. So this would be when this attacks there, it goes through a bridge system, so that you would be forming a dibromo. The reagent would form this bridged system. So now the Br would come from anti-position, meaning that's different from the stereochemically. So this would form from the highly substituted position. So Br minus would attack. It forms a dibromo compound. So you'd have Br opens, this opens back, Br would be here, and you have that carbon, which is this one, another carbon, 1, 2 carbon, and the third carbon, and OH. So you'll form this dibromo compound from bromine addition through a bridged intermediate. That's what I want to emphasize here. But as you see, this has undergone through a cyclization. So the cyclization should happen by way of making a 5-member ring. So if you just count this 1, 2, 3, 4, and the bond, that would be attacking this by SN2 mechanism, and OH would attack that position for cyclization. So that is a bromoetherification process. Etherification by SN2 could be a plausible mechanism. That's a reasonable mechanism to assume that this would attack that and this go out. And then the Br minus would, once you have here you have this O and H here, obviously, and plus, and you have Br minus, Br. So the Br would minus, which is a nucleophile around, would grab that proton, neutralize it in a bromoetherified compound, which is Br. So that's how it happens. So it's very interesting how this end up. So go through bromine addition through a bridge bromonium ion. The bromonium ion would open, it forms a dibromo compound, and since 5-member rings are stable, this OH intramolecularly make an SN to attack to this carbon right here. This leaves to make that compound. So that's very interesting how that is cyclized. Initially, you should know this is the initial step, which was very important. You should remember that bromine, molecular bromine, adds to the double bond and forms a dibromo compound. The dibromo compound hanging around there, the OH is in the molecule itself, so it can come and attack to form. So it's a very reasonable mechanism. We proposed how that's formed. So usually the question is, would be asked that propose a mechanism. So for this, the question is, propose a mechanism, how that is formed. So this is a typical question you would get in organic chemistry. Propose a mechanism, how that's formed. So we proposed a very reasonable electron or arrow pushing mechanism for this reaction. Okay, we'll continue more on synthesis. So the final few slides or few sessions in the session would be focusing application of synthesis in our final video, which the next chapter would be alkynes, not alkenes, and sp hybridized alkyne would be our next chapter. Before I continue to the next chapter on alkynes, as a conclusion of this chapter, I will solve some problem on synthesis. I will introduce you to some lighter, easy synthesis problems. Okay, now so far we have learned mechanism of reaction, addition reaction on alkenes, their stereochemistry, rearrangements while formation of carbocation. Now, almost in the final phase of our chapter, I'm going to introduce some aspects of synthesis. That means the application of what we learned, how to synthesize molecules. Here I have 3 molecules that are synthesized from starting materials of this nature. And now from what you have learned in alcohols chapter, that is chapter 9, and chapter 10 from alkenes, how do you make this compound, for example this one, from this? So let's always, when you begin analyzing to come up with the synthesis plan, you see the product. So now the product and the starting material. The starting material is alcohol, a primary alcohol, but it ends up to be this alcohol, which is a secondary. This is a pentanol, 2 pentanol versus 1 pentanol. So how do you convert to that? The OH cannot just jump and come here. So what do you do? The synthesis strategy I would outline would be, this can be done by hydration of an alkene, right? So an alkene would produce this final product. How do we do that? First, to get to an alkene, you need to dehydrate this. So what are the dehydration step? Dehydration. After dehydration, if you do hydration, reverse it, you could end up getting this molecule. So that is the main strategy. So for dehydration of alcohols, for example, phosphorus oxychloride has been used, if you remember, in chapter 9. So the way I would start doing the synthesis would be 1, 2, 3, 4, 1, 2, 3, 4, 5 OH. I would add dehydrate using phosphorus oxychloride. That would dehydrate it into 1, 2, 3, 4, 5. This alkene. So once I have that alkene starting from this, that's the dehydration step, I would hydrate this using sulfuric acid and water. As you know, the carbocation would form on the secondary carbon, not here. Therefore, the OH can come exactly where I want it. So that's done. This is the reaction of first dehydration. After dehydration, hydration would give me this. So you have to think how to go about certain things. So this is at the outset, when you see it, it looks like very difficult to see how that OH would go to that position. But from alkene subject we have learned, and also from hydration of the reaction, you could make that compound. Let's see here. This is a bromo compound. It is a 2-bromo-propane. This is named as 2-bromo-propane. But here you would see a compound that has a dibromo compound. Oh, you don't have this. We don't do that. We don't have that. So this is 1, 2, 3. That is 2, 3. That's how it is. So how do you make that compound is the question. So obviously you have to go, if you want to have a dibromo compound, somehow, if you remember, addition of bromine results in dibromo compound. But addition of bromine to a dibromo comes from an alkene again. So you should get an alkene from this alkyl halide. This is an alkyl halide. So if you remember our chapter 9, or I think in substitution reactions, by elimination reaction of alkyl halide, we could end up getting an alkene compound. So if you treat this with a strong base, a strong bulky base, by E2 elimination, potassium tertiary betoxide, for example, would give me an alkene. That is, you would eliminate, this is the alpha hydrogen is this one, this is the beta hydrogen, so this is the alpha bromo that would leave, so I would get this compound, CH2. So I would get the elimination of one of the hydrogens to give me CHC2. To this, if you just do addition reaction of Br2, voila, you get this. Very easy. So you make an alkene first and do addition reaction, you get the dibromo compound. Revise again this one, dehydrate this using phosphorus oxychloride. That's why you need to remember the reagents, and addition would give you to that compound. Okay, C, if you see the product is a bromohydrine. How do you synthesize bromohydrines? For bromohydrines, we remember alkenes can be transformed into bromohydrines. So again, what I'll do is I'll eliminate to make an alkene here. I'll use a strong base, potassium tertiary betoxide, for example, would give me an alkene. Then from an alkene, I can use bromine in water or NBS in DMSO water. This would give me a bromohydrine. That's it. Two-step. All of these are two-step reaction so far. They are not multi-step. These are easy. Just two steps. Here, for example, elimination. That's in E2 reaction. And here is a bromo addition to the alkene, bromohydrine. So this is bromohydrine formation, bromohydrine. OH and Br are added. So you just saw a very light, easy two-step reaction in the synthesis of these products. Okay, we'll continue more on synthesis. Okay, more on our synthesis problems. Continuing here in this problems, there are two problems here, starting from cyclohexene, which is an alkene, and here we are forming an ether. So we are asked to propose how do you end up into this using multi-step synthesis. So from the outset, what you see here is this ether is an ether functional group. So ethers, if you remember in chapter 10 of our video series, ethers can be synthesized using Williamson ether synthesis. That means it can be synthesized this by Williamson ether synthesis. For Williamson ether synthesis, you need an alcohol. Okay, that is the point. So how do you get a single alcohol on this molecule? Very easy. First, hydration, sulfuric acid, water would give you hydrated product, which is OH. You get the alcohol. Now, if you see the alcohol, if you just cut it right here, you need to have a bromine here or the OH there. So now, if you have the OH on this, what you need to have is an alkyl halide, which can be used as a SN2 reaction. I can react this with a bromoalkyl halide, which is a 3-carbon one. So if this attacks by SN2 on this one, which is a Williamson ether synthesis, an alcohol would give me the ether. But the alcohol is not strong enough to kick out the bromo compound. What we have to do before that is, first, we have to take off that proton using sodium hydride to form the alkoxide. So the alkoxide is formed, O minus. So O minus now, this would not be doing it as it is. So O minus reacts with the alkoxide, the cyclohexene oxide. This would attack that. That would do a good SN2 to give this product. This is called Williamson ether synthesis. Williamson, the second step at least, is called Williamson ether synthesis. You need to revise that. That is made from an alcohol using a strong base like sodium hydride. You could have an SN2 reaction to form that. So the first step, these are two steps. You hydrate first the alkene and then do the ether synthesis. Here I have a thiol and a hydroxy compound from the cyclohexene. So I think what I see here is this is a nucleophile. Okay, that nucleophile would be substituting a bromo compound. So if I have a bromo and a hydroxy, that can be done by a nucleophilic substitution. So what I will do on this one, here you see the issue is the stereochemistry is well defined. This OH and this SH are trans in the product. That's what you need to get. So if we were to do bromohydrines, we cannot do it, because if you, for example, have a bromohydrine, meaning that bromine in water, you would end up making a hydroxy, for example, up and a bromine down. And if you were to attack this with a nucleophile, SN2 nucleophile, SH, attack this, this gives you this product, OH, and it would give you this, SH, because it's backside attack. So that's not what you have. So this is not the right stereochemistry. So what I would propose would be, instead of going through bromohydrine, I would go through dibromo compound. So from cyclohexene, if I do dibromo compound, which would give me an anti-addition, one bromine is up, one bromine is down, and then by SN2 reaction, if I do SH nucleophile, it can attack, if it attacks this from backside, no, so that's a bromo compound. So first what I need to do on this one is to do an SH nucleophilic attack on this. Okay, let's say it would attack from back, or so they will end up making in the same side. That means I can have SH and BR like this. So, because that's if it's backside attack, you would end up getting that. So then, now if I just do a nucleophilic substitution with sodium hydroxide on the bromine, that would be a backside attack, which gives me an OH and SH. So this is a little bit complicated, but this is what I would propose. First, go through dibromo addition, which would be trans, and make a nucleophilic attack, which would be syn. Both of them would be in the same side. And then if you do hydroxide attack on the bromo, you could end up getting a trans. So that's a proposal. If you come up with another plan, that would be still acceptable. I'd like you to give me a comment on the video comment section. So that would be the second synthesis. So here we did hydration, following by Williamson ether synthesis to go to this. Here we did two switching off of nucleophilic substitution, initially by dibromo compound added. So this is the step I would take, because we want to keep the stereochemistry of the final product as well. Okay, we'll continue more on this. Okay, still we are continuing on synthesis problem. Here I have this alkyl halide, which is a 1, 2, 3, 4 carbon, 1, 2, 3, 4 carbon compound. So the question is, how do you synthesize this epoxide? This is an epoxide, obviously, starting from this compound. So if you remember bromohydrines, like through Williamson ether synthesis type, epoxides can be prepared. So the first thing is, this is a starting material, starting from this. How do you go to that product? So how is this made from this? That's the question. So this is a backward, this is called retrosynthesis. The arrow I am showing here is called retrosynthesis. That means you see the product and you come back to the original, or you go in the forward. So this is a backward synthesis. So in the retrosynthesis of this, for example, I'll just try to introduce you now. This epoxide can be prepared retrosynthetically this is backward. So I would just say, for example, if I have a bromo here and OH there, so that can close and make that epoxide, right? But how do also I make, so now I'm going retrosynthetically backward. So how do I do bromohydrins like this? Retrosynthetically, bromohydrins can be synthesized from this alkene, right? How about this alkene? How can we synthesize this alkene from here? Yeah, there is a way how to synthesize this alkene from this. So that could be done by elimination reaction. So starting from that, let's do now the forward reaction. In the forward reaction, to come to this now, these are retrosynthesis, backwards. We can also now do the forward. Now I'm writing the synthesis, not the retrosynthesis. So starting from this, how do I go to the alkene? Alkenes can be made from elimination by E2 of an alkyl halide that we have done, I think, in chapter 7 or 8. So if I do that, I have 2 carbons there, bromine. If I use a very strong base, potassium tertiary butoxide, for example, that would give me this product. That means the elimination would give me this alkene. So I am providing the reagent how to proceed in the synthesis direction. From this, what we are looking at is the bromohydrin. How is bromohydrin synthesized from this alkene? We have to provide a reagent now. The reagent would be NBS, DMSO, water. That is, bromohydrin can be formed from this. So now the bromohydrin that would be formed looks like Br here, OH here. Okay, so far so good, right? Now to go to the epoxide from here, first if I pull off that proton to make it ready for Williamson intramolecular SN2 attack on this carbon, if I treat this with sodium hydride, I'll make a very strong nucleophile, O-, Br. Now this would not be stable. I mean, it would attack that by SN2 reaction, intramolecular SN2 reaction, that closes to the epoxide. So these are the forward synthesis. This is the retrosynthesis. Retrosynthesis is you go back each step until you reach to the starting material. That's the retrosynthesis. Once you figure out the retrosynthesis, now you go for the synthesis, how you come up with that each time. So this is some of the strategies we use in synthetic organic chemistry. So I really ask you to revise and exercise similar questions. Okay, we'll proceed with one more question, and that will conclude our alkenes chapter. Okay, in this final question, you see here this alcohol is converted to B or to C, and the question is you are required to design a synthesis, multi-step synthesis. Obviously cannot make it in one step. So how do you synthesize from compound A, let's say, to make these 2 different compounds? So for this, the way we have to proceed, for example, if we were to do compound B, and if you want to do a retrosynthesis analysis of B, okay, let's say you have compound B here. The retrosynthesis analysis at least would suggest to me, if I put some alkene here, obviously, that could be converted into a bromohydrine, and that can give me the epoxide. So if I have something like this, some alkene here, that is a good starting point to bring the double bond and the oxygen on this. So how do I get from this to this? It is simply a dehydration. So this would be starting from A. Now I'm doing, this is retrosynthesis, So in the forward direction, starting from there to reach to this, first I have to go to this alkene. So if you remember what we have done in dehydration reaction, you remember what we have done. If you use POCl3, for example, okay, you could dehydrate this and make a more substituted alkene, which is this. This is CH3, so dehydration, loss of water, right? So that gives you that alkene. To go to this epoxide from that alkene, if you just do NBS, DMSO water. So this is bromohydrine. For epoxides, you start from bromohydrines. So what you will have would be, if you have OH here, and bromine would be right here. You are adding bromohydrine across the double bond. Now, if you just apply Williamson ether synthesis, sodium hydride, you could close that epoxide and form this, which is compound B. That's done. So that is the forward synthesis for compound B. So starting from here, how do you also make compound C? So so the only functional group we have is this OH. So if I dehydrate this, and start from this one, for example, the double bond would be outside. But here the double bond where the epoxy is formed, if I do retrosynthesis to this, for example, the retrosynthesis of this, I have to have something like this, right? Because then if I just follow this step, I can make the epoxide right, that double bond, right? But how do I get that double bond inside? But my reactive species is outside. No problem. First, what I will have is, let's start from here. Let's start from here to reach to this. So if I have this alkene, because we know how to get to this, so if I just do the same thing, OH, and if I do dehydration, I will have the same alkene like that. But at this point, what I need to do is, since I want the double bond to be here, what I will do is I will hydrate it again. So during dehydration, using sulfuric acid water, the OH would be on the more substituted. So hydration, sulfuric acid and an acid would give me OH right there, and this. So I will have that. So once I have that actually, instead of doing this and to use elimination reaction, sorry, I will take that back. And instead of hydrating that one, the strategy should be better if I add HBr to this instead of this. Okay? Forget this. You might try that at home, but let's do HBr addition. So if I do the HBr addition on this one, the H would be on this, and Br would come there. I think that's a better strategy, I would believe. H and Br would be here, right there. Okay, then if I have Br over there, the next thing is to eliminate that Br. So if I use this beta hydrogens and use strong base, potassium tertiary butoxide, E2 type elimination, I would make the double bond right here. So that way I will have double bond here and that. So basically I am right there. After that it's very easy, because I can just do, once I have that, we can, so I will just move here, do NBS, DMS, or water. I think that should give me bromo alcohol. Okay, so that would be OH here, and bromine here would be added from this. Now, if you just do Williamson ether synthesis, pull off that proton, that would cyclize to make the epoxide we want. So it ends up here. So that concludes the synthesis of the second one. So here, A, compound A. From A, we were able to make B, and we were able also to make C. So that is multiple synthesis, which is very exciting to see how we could synthesize these molecules. And with this, we conclude chapter 10, which was dealing with alkenes and their reaction mechanisms, stereochemistry. It's a very huge subject matter, an alkene. And now, in the next video series, the next lecture would be starting from alkynes. Okay? With this, we conclude chapter